let's have a look at the concept of ideal versus real gases. To do this, we need to establish our relationship for the ideal gas law. So PV equals nRT. If we hold the number of moles constant and the temperature constant, we know from our work on Boyle's law that as the pressure increases, the volume will go down. Now we can rearrange this equation so that we get PV over nRT, and if we rearrange that for any given pressure and volume relationship, our PV over nRT will always be 1 if we plot it against an increase in pressure. So pressure goes up, volume goes down. This will give us a value of 1 as we move through. So this is our ideal gas law situation, and it should apply to all gases. However, when we measure it, if we plot a graph for a gas like chlorine, we find that we get that sort of graph. If we do it for another gas like helium, we actually get a relationship like that. So this tells us that if we increase the pressure, hold the number of moles and the temperature constant, we're not getting anything like our ideal gas law. So before we look at can we use it, let's think why this happens. Well, if we remember back to kinetic theory and how it applies to gases, we made 2 assumptions. First of all, we said that molecules have negligible volume, or molecules of gas have negligible volume within the molecule compared to the overall volume. So in other words, the volume of the individual molecule doesn't contribute to the volume of the gas. But as we know, all atoms and all molecules have a volume, therefore they should contribute to this total volume. Second of all, we said that there were no interactions between molecules. There were interactions between the gas molecules and their container, but not between molecules. We know that that's incorrect as well. So does this put our ideal gas law equation into jeopardy? Let's have a look. In other words, can we use the ideal gas law? Well, it turns out that yes, we can, as long as the temperature and pressure are not extreme. So at very low temperatures, our ideal gas law does not apply strictly. We've also got, at very high pressures, the gas law doesn't apply very well either. Now, combined with that, if we really wanted to, we could use a correction that Van der Waal came up with to correct for our real gas. So he changed our original equation, which was PV equals nRT, and made some correction factors. First of all, he said that our pressure, we needed to take into account the number of moles or the number of molecules that we had, and we had to correct for the interactions within those molecules. We also had a correction for the given volume of space as well, or the volume that the container's in. So that gives us our P. We also need to correct our volume as well, and once again we have a correction for the number of moles or number of particles of gas that we have, and we also need to correct for the size of the molecules, in other words, the volume of the molecules. So our equation, rather than being this one here, is a corrected equation, and it applies for all gases because A and B are different for every type of gas.